All right, so this is week 3 already. Section 5.2, this is page 9 in your notes, if you can find that. And you can just go ahead and read about the definite integral, but it has a lot to do with like what the Riemann sums we did last week. But what we're going to approach is infinite rectangles. So if you imagine infinite rectangles, it's like almost that it's totally shaded in and it's not an estimate anymore. And you can go ahead and read that. It's really important that you always have this dx at the end. And it was kind of like a light bulb moment to me in one of the videos. What that relates to is that you're drawing your rectangles or your area down to the x-axis. So I thought that was kind of an interesting thing to know. So at the bottom, here's just some, I have to look back at this a lot, so keep this page handy. This is talking about like if we go from 1 to infinity, or actually not infinity, 1 to any number, like 1 to 5, for example. This means that you would add 1 plus 2 plus 3 plus 4 plus 5. Well, a shortcut method to do that is you can use this formula. All right, we have formulas for I squared, I to the third, just a constant c, c times xi, and then here just adding up different limits. You're allowed to, or different summations, you're allowed to separate them. So you can just kind of keep this page handy because we're going to use this a lot. So the first one that we are going to evaluate is on the next page. This is page 10, and this is example 1. I watched lots of videos, and I thought the video that was most helpful, he kind of broke this down into steps. So taking this formula here that we have on page 9, this is our goal, is to take this integration and write it as this limit problem. And he kind of broke that down the steps. Step 1 is to find your change in x. So that's just your b minus a divided by n, and we did that some last week. So it's just the top of the integral minus the bottom, and then divided by your n rectangles. The second thing you want to do is apply an I, like x, the I term of x, and you just, to do that, it's pretty easy. You just take your starting value a plus I times the change in x, and that's what you're always going to plug in, but a is going to be a different number depending on what problem you're on. The third thing you're going to do is then take whatever you get here for this xi and plug it back into your function. So right now our function's x squared. We would plug whatever we get into x squared. And then you would just kind of put this all together and you would evaluate with the summation and the limits. And that's kind of tricky, but the more you do it, the easier it gets. Okay, so let's go ahead and get started on this problem. So for number 1, the change in x is b minus a over n. So b minus a is just 2 minus 0, which is 2 over n. So that's easy. So 2 over n. Okay, so again, it's just 2 minus 0 over n. Xi, we're going to apply this, a plus I times the change in x. Well, our a is just 0, so I don't even really have to write it down, but I will just to do it, plus I times 2 over n. So how could we just kind of write that a little bit more concise? We don't really need the 0, and then I times 2 is 2i over n. And this is the I term. Don't get us confused with the imaginary number I. Now let's plug this into our function. Well, our function is just x squared. So all we have to do is 2i over n squared. And if you want to write that right now as 4i squared over n squared, that might be helpful. Okay, now step 4 is to plug all of this in. So limit as n approaches infinity as I goes from 1 up to n. So it's like, okay, so what I did is I'm just plugging in this green formula. So limit as n approaches infinity as I goes from 1 to n of our function, and it's 4i squared over n squared times just the change in x, and the change in x is 2 over n. So I'm going to go ahead and multiply these things together and get 8i squared over n to the third. Okay, now what we want to do is take everything out in front that does not have an I involved with it. Okay, so I chose to write the 8 over n to the third in front of the summation sign because all this really affects is just any term that has an I, as I goes from 1 to n. So really all that we care about here is the I squared. So if you look back on page 9, find what we know is true of the summation of I squared right here. is n times n plus 1 times 2n plus 1 over 6. And I went ahead and just FOILed all of that and have 2n cubed plus 3n squared plus n over 6. So this is now what you can plug in. You can replace all of the summation of I to the second with this right here. So we still have the 8 over n to the third, but again, we're replacing the summation of I squared with what that equals. 2n to the third plus 3n squared plus n all over 6. And now what we're going to do is I'm just going to go ahead and multiply these out. And now it just is becoming a limit problem. So we'll have 16n to the third plus 24n squared plus 8n, gosh, I'm really sloppy, over 6n to the third. So now if we're taking the limit as n approaches infinity, we have lots of infinities. We have infinity divided by infinity. All right, sorry, I kept messing up. So again, we were right here. I'm gonna zoom in a little bit. All right, and notice that we could divide everything in the numerator and the denominator by n. So that just kind of simplifies it down a little bit. Again, we're still applying the limit as n approaches infinity. So we still have infinity over infinity. So we're going to use L'Hopital's rule, where you just take the derivative of the numerator divided by derivative of the denominator. So 32n plus 24 over 12n still is infinity over infinity. So apply the derivative again, and you get 32 over 12. Or 8 over 3. I'm going to show you how we can check our answer. And again, what this means is x squared, you guys know it's just a parabola from 0 to 2. That green shaded region, I have shaded 8 over 3 or 2.6 repeating. That's the area under that curve. So let me show you how you do this on Desmos, and it's really, really easy to check your answer, but you still are going to be required to show all this work. Okay, so this is the answer here, but I'm going to show you how I got that. You just start typing an INT, and then the symbol appears, and then from 0 to 2, like this, and then arrow over, and then x squared, and then arrow over, and you have to type in dx or nothing happens, and there it is, 2.6 repeating. Here is example 2, as we go from 0 to 3, 2x minus 1 dx. So our change in x is just b minus a, 3 minus 0 over n, so 3 over n. So that is our change in x. Our x sub I, remember, is a plus I times the change of x. Well, our a is still 0, and you can look at the math here. I have 3i over n. That's my x sub I. Now if I plug that into my function is 2x minus 1, so I have to take 2 times 3i over n minus 1. And now I'm going to apply the whole rule where you take the function of xi times the change in x. So again, here's my function of xi, and here is my change in x. So looks like I just did distributive property here with the 3 over n, 18i over n squared minus 3 over n. And then this term right here, I took the 18 and n squared out front, leaving me with just an I. Now I know this looks weird, but you still have to write that summation notation, but with just a 1. And then if you look back at page 9, all that happens is as I goes from 1 to n times 1, the answer is just going to be n. Okay, so this is applying the summation. Here, applying the summation of I plugged in n times n plus 1 over 2, and I need to multiply it. It looks like I canceled out an n, leaving me with distributing 18. 18n plus 18 over 2n minus just the number 3, because see how these n's cancel? And I'm still finding the limit as n approaches infinity. I did L'Hopital's rule and got 18 over 2, which is this 9, and this 3 stays. So 9 minus 3 is 6. I also wanted to show you how we really simply could find the area just by using geometry and algebra. So the equation 2x minus 1 starts at negative 1 and rise 2, run 1, just a line. And I want to go from 0 to 3. This we'll talk about on the next page. So this is called negative space because it's below the x-axis. So the area of that little triangle is negative 0.25. The area of this big triangle is 6.25, and you can see clearly those do add up to 6. Here's example 3. I advise that you try it. Just kind of look at my work and check over this, and you really are going to learn it if you try doing it. It took me a long time to wrap my head around this, so I think it's going to be the same for everyone else. Let me keep scrolling down here so you can hopefully pause and try this problem, but the answer ends up being 18. And then I showed you geometrically why the answer is 18 as well. So again, we're talking about a straight line, but only from 2 to 4. And then if you found the area underneath that curve, it's not really a curve, under that segment, the answer would be 18. So hopefully that helps studying over example 3. All right, page 13. This just talks about this positive and negative area. If the area is above the x-axis, if it's positive. If it's below the next x-axis, it's negative. Example 4 is given. You can kind of read that over and it'll probably make sense. But our answers should be -2, -1, and 3. So I advise you try that. And I believe we have one more question, one more thing to talk about. This one's easy though. So example 5, find the net signed area of f of x equals 2x in the x-axis over the interval -3 to 3. Use geometry, and we've done enough of the definition, so I crossed that part off. So if you guys just look, if we were going 2x, that's just a line like this, and we're going from -3 to 3, it forms these triangles. This is 3 by 6, and remember it's base times height divided by 2, so it'd be 3 times 6 is 18, divided by 2 is 9, but since it's below the x-axis, you write that as -9, and this is exactly symmetrical. This is +9, so the total area is 0. So hopefully that makes sense. Your homework questions are page 383, 21, 25, and 35. You need to show your work. You can't just show the answer because it's in the back of the book and you can do it on Desmos. So good luck, and email me if you have questions.